autoencoder. Autoencoders are deep neural networks used to reproduce the input at the output. Thus, the number of the outputs must be the same as the number of the inputs. The goal of an autoencoder is finding a representation of the input in the output such that they are too close to each other. But the actual use of an autoencoder is for dimensionality reduction, such that a compressed version of the input is found and the most important features are extracted in the hidden layer. The number of the features that we would like to have is optional, and it actually depends on the problem that we are trying to solve. Here in this slide, we name a few of the applications of autoencoders. Autoencoders are widely used with the image data, and some of their use cases include the following: dimensionality reduction, image compression, image denoising, image generation, and feature extraction. In this slide, you can see two neural networks. The neural network, which is shown in figure A, represents the most common structure of the autoencoders, in which the hidden layer has fewer neurons compared to the input and output. However, in some types of the autoencoders, the hidden layer could have even more neurons than the input and the output. These specific autoencoders will be discussed later in the upcoming slides. The network shown in figure B could also be thought of as a specific autoencoder in which there is no limitation on the number of the neurons in the hidden layer. Here in this slide, we are going to review some of the most important details about autoencoders. An autoencoder is an unsupervised learning algorithm which uses the backpropagation method in order to learn the weights and extract the most important features in the hidden layer. Its target is to learn a model which gives an output that is very similar to the input, considering the constraint that we have on the hidden layer. It tries to learn the model for the identity function, which might seem not very useful, but by limiting the number of the neurons in the hidden layer, the model learns great facts about the structure of the data. If all of the features are independent at the input, then the autoencoder is of no use since it cannot compress the data in the hidden layer. But if there is a kind of correlation between the features at the input, the autoencoder can work as a feature reduction method to learn the compressed representation of the data. It's good to keep in mind that the ideal autoencoder is the one that has the following features. It must be sensitive enough to the inputs to accurately build a reconstruction. And it also must be insensitive enough to the inputs that the model does not memorize the inputs and does not overfit the training data. There are different types of autoencoders: the undercomplete autoencoders, the denoising, the sparse autoencoders, variational autoencoders, convolutional autoencoders, regularized autoencoders, multi-layer, and the vanilla autoencoders. And this list goes on and on. Here in this slide, we are going to discuss about one of the types of the autoencoders, which is called undercomplete autoencoders. In this type of the autoencoders, the number of the neurons of the hidden layer must be smaller than the number of the inputs and outputs. By penalizing the network according to the reconstruction error, the model learns the most important attributes or features of the data. For the purpose of feature reduction, autoencoders are better than PCA or principal component analysis method, since they are able to learn a manifold, or in other words, a complex representation of the data, while PCA only learns a hyperplane. A manifold is a non-intersecting topological space. In the undercomplete autoencoders, we must make sure that the model is not memorizing the training data. That's why we put limitation on the number of the neurons in the hidden layer. Another type of autoencoders are denoising autoencoders. In order to make sure that our model is generalized and is not too much dependent on the training data, we can slightly corrupt the input data and keep the uncorrupted data as a target in the output. The model will be trained such that the weights are learned to cancel out the noise to make the input similar to the output target. In this way, the model is forced to learn the robust features that tend to generalize better. Such autoencoders that have to cope with the distorted input to make more generalized outputs are called the denoising autoencoders. In this slide, we are going to talk about another type of the autoencoders which are of great importance. This specific type of autoencoders are called sparse autoencoders. In this case, we can violate the previously mentioned constraint on the number of the neurons in the hidden layer. In other words, we assume that the number of the neurons in the hidden layer are equal, or they can be even bigger than the number of the neurons in the input and the output. The idea behind this is to keep most of the neurons inactive, such that their output is equal to 0. Thus, this will make the hidden layer sparse, and that is why these autoencoders are called sparse autoencoders. This idea of deactivating some of the neurons is also behind adding the dropout layer, which is used in neural networks to prevent overfitting. One of the examples of the sparse autoencoders is the K-sparse autoencoders, in which the model finds the K highest activations in the hidden layer and zeroes out the rest. In K-sparse autoencoders, for large K, which shows low sparsity, the features are more general, but for small K, which corresponds to high sparsity, features show the local properties of the image. Here you can see an example of a sparse autoencoder in which the number of the neurons in the hidden layer Z is even bigger than the input X or the output X hat. Here we are going to explain the math behind the sparse autoencoders. Consider the following formula, the first formula, in which the A superscript 2, X, rho, and M are the activation function of the hidden layer, the input, the sparsity, and the total number of the training samples, respectively. In sparse autoencoders, we try to set the sparsity parameter equal to a very small number like 0.05 to make most of the neurons in the hidden layer inactive. The smaller the rho, the more hidden layers being inactive. We also want to penalize the case in which the sparsity parameter is far away from the small value, like the sparsity value 0.05 here. So the second formula that you can see here in this slide shows the callback labeler or KL divergence. It shows how far away two distributions are from one another. Since the target sparsity parameter is small, we also want the rho to be small. So we need to minimize the KL divergence as well as the cost function. So the overall cost function to minimize is as what you can see here in the third formula. The parameters J, W, and B show the input-output error minimizer, the weights, and the bias of the hidden layer. By minimizing this total cost function, we would be able to find the weights and the bias values that would provide us with the sparsest hidden layer.